In this video, we'll look at the concept of duality. This is a geometric transformation that transforms a line into a point and a point into a line. This is useful because in many problems, once we do the duality transformation, the problem changes sufficiently that we can then solve it. In some sense, this is just a cosmetic transformation. You can always solve the problem without using this transformation. And in particular, when you want to code like a solution, you don't need this duality transformation. But what it does is that it makes the problem sometimes easier for us humans to solve. There are many problems that when we think about them as humans, we cannot see a particular structure that the problem has without using this duality transformation. We're going to look at a bunch of examples later on that will show some of these examples. And then you can see that how using a simple duality transformation will change the nature of the problem so fundamentally that you can easily see the solution. Whereas in the original formulation of the problem, the solution would seem impossible to find for us humans. But once you do the transformation, then it becomes easy to see. So let's just look at what the transformation does. So here I'm assuming that I am representing lines in this format as y equals slope times x and then plus the y-intercept. So what it does is that this duality transformation transforms a point px, py into a line given by this formulation. Okay. And similarly, if you have a line ax plus b, it transforms it into a point given by a and minus b. And if you look at these two formulations, you'll see that the dual of a dual will be this the object itself. In other words, if you start with a point px, py, you get this line, y equals pxx minus py. And once you do this transformation on it, you get px and minus pi, which is py. So in other words, the dual of a point is the point itself. Okay, so it's essentially a one-to-one correspondence. This duality transformation has a bunch of properties that are very useful. We're going to prove them in the exercise classes. The proof is actually very easy. But let's see what it does. The first property is that if you have the first property is that it maps a point to a line and it maps a line to a point. Okay, so that's easy. The second property is if you have a line L in this primal space, which is before we do the duality transformation, and you have a point Q that it lies on the line L. Once you do the duality transformation, the line L will turn into a point, let's say L star, and the point Q will turn into a line Q star. And the interesting point here is that if the point is on the line, after doing the transformation, the point will still be on the line. Of course, the role of the point and the line changes, but still you have a so-called incidence. If the point is on the line, then the point is still on the line. The same thing holds for the below and above relationship. So here, let's go back one more and you'll see this example here. I have a point P that is below the line L. After I do the transformation, this belowness still holds. In other words, the point, which is the dual of the line L, will be below the line, which is the dual of the point. Okay, so after doing the duality transformation, the point will turn into a line, the line will turn into a point, and this relationship is preserved. These are essentially the only two properties that we need for this transformation. The exact formulation of the duality transformation is not so important. And in fact, there are multiple ways to define a formula that does this duality transformation. So we don't actually care about the exact formula, especially because in most applications you don't even need to do this transformation anyways. It's just, as I said, cosmetic. But what we're interested in is those two properties. So for example, let's look at one example of what this transformation buys for us. So here's again more examples of duality transformation. So if you have a picture like this, then by just using the properties that I listed, we can reason about the dual representation of these objects. For example, the point R is below the two lines L and M, so therefore the line R star will be above the points M star and L star. Similarly, the point P is on the line M, so therefore the line P star will go through the point M star. Similarly, Q is above line M, so therefore the point M star will be below the line the Q is above, so therefore the point M star will be above the line Q star, and so on. So by just looking at the structure of this, the relationship of the points and lines on this primal space, I could know how the picture looks like in dual space, and that's going to be very useful for us later on when we try to form the dual of some of the well-known problems. Okay. One observation that here we could make based on this particular definition is that if you have two parallel lines, since their slopes are the same, the dual will be a point will be 2 points out of the same x-coordinate, which means that the dual will be essentially vertical like that. It's going to be, the 2 points will be on top of each other. And finally, let's look at this example here. If I look at a line segment PQ, what does this line segment, how this line segment will be represented in the dual space? Well, first of all, if I have these 2 points, when I look at the dual, I will have a line Q star and I will have a line P star. Their intersection point, let's call it L star, is the dual of the line that goes through them. Okay, so the line L that goes through points P and Q will be dualized to a point L star that is the intersection. This is because from every 2 point there is a unique line that goes through, and therefore and this line has to be incident to both of these points, which means that on the dual space I should have a point that lies on both of the lines, and there is only one point that has this property, which is the intersection point of the two lines. Okay, so again, this follows by the incidence preserving property of the dual transformation. But more interestingly over here, I'm interested in what happens to the line segment between P and Q. What we can observe here is that if I take a point that is between points P and Q, what does this correspond to? I think I have a picture. Yeah. Okay, so I take a point R that is in between. What does that correspond to? If I just reason about the particular definition of duality that I use, the x-coordinate is between the x-coordinate of P and Q. So therefore its slope of this line R star in the dual will be between the slope of Q star and P star. So it has to look something like this. So now imagine I take all the infinite points that between P and Q and I dualize all of them. I will get a set of infinite lines that pass through L star, and the slopes cover all the slopes between Q star and P star. So therefore I will get this shape here, this pencil of lines. So therefore the dual of this green line segment, if I look at this line segment as individual points, is a set of lines that pass through L star and between these two lines. Okay. So again, that's one example of how we can form the dual of a slightly more complex object by just reasoning about the specific properties of this duality transformation. In separate videos, I talk about projective planes, and the notion of projective plane is going to be very powerful in understanding the concept of duality and relationship between different objects. For example, if I use the representation of y equals ax plus b to represent lines, then we all know that I cannot represent vertical lines. So therefore you might wonder, what the hell is the dual of a vertical line? Don't you say that a duality transformation will transform a line into a point? If I cannot represent these lines, how do I find the dual of them? The answer is that if I just stay at this Euclidean space without going to the projector plane, I cannot define the dual of every line. But if I go to the projector plane, then you can actually find a dual for every single line. But again, I will leave that for the exercise classes. And that basically concludes this video.